Now we'll talk about logical clock and vector clocks. So we have seen in the previous lectures that a physical clock are a way to timestamp time, and physical clock can be obtained when there is a synchronous system. So it's possible to get clock synchronized, and this synchronization is more or less accurate up to some bound that is given by the synchronization algorithm, and this bound is unavoidable, and is due to the fact that the system has delay that are not exactly predictable even when you are in a synchronous system. So you have a maximum delay and a minimum delay, but you cannot predict the actual delay of a message. And clocks are used to timestamp things, usually in synchronous system, and they create an almost total order of timestamp up to the accuracy that is given by the synchronization algorithm that we use. But what we need is a way to have some kind of logical clock that give us a partial order of event even on a synchronous system. And let's motivate our study with an example. And we will see that there are examples where having this ordering is important because it avoids some pathologic situation. And so the scenario that we study is a distributed chat that is used in a mission critical workplace. So for example, a nuclear power plant. And why is it has to be distributed? Because there is no central point of failure, and because there are privacy concern and there is need of confidentiality. And so we have that no server can store encrypted copy of messages, and there are no metadata records of the message that are stored. And this can be achieved by a totally distributed algorithm because we don't have centralization. Then we assume that the model is asynchronous. And why we have to assume it? Well, because it's a mission critical environment and it has to work even if the system loses synchrony. And there could be several reasons why we lose synchrony. One can be that we have adversary in the routers. Another is that we have network defect, so as example, broadcast storm. But anyway, since our scenario is mission critical, we need something that works even in a synchronous model. And the problem is that we cannot synchronize and we cannot timestamp with software clock because the model is asynchronous. And a naive solution to implement your chat application is the one of just sending a message to everyone, and then when you receive a message, you authenticated it and you deliver it in upper layer. And this thing works in the sense that you know that the sender is the actual sender, and you know also that the message has not been tampered. You can also encrypt messages if you want them to be confidential. The problem is this example. So let's see that there is this group chat, and we have a manager that says tomorrow we have a security scenario, a security test, and we have to create a doomsday scenario. So a really problematic scenario for our power plant. And Tom says we can try to fake a core meltdown. And then the manager says, good, Karen, start with creating an example. And Karen says, core temperature is increasing and the core temperature is at critical point. And now the manager asks Mike, what we should do in this case? And Mike says, we should release the vapor and we have to avoid the explosion at all costs. And then Bob's supervisor says to Bob, release it now. The problem is that asynchrony kick in, and this order of messages is not the same for all the participants that are in the group if you just deliver message by delivering whatever you receive. And the problem is that Bob local view can be this one. So Bob receives just the messages of Karen, then the message of Mike and of his supervisor. And the problem is that Bob is totally oblivious of the things that the manager said. He does not know that this is an exercise and is a simulation because he didn't receive the messages from the manager and from Tom. And this can happen because in asynchrony we have an adversary that decide when an event or message is delivered. And if we implement the chat the way we have said, in a naive way, this example is possible. And the problem with this thing is that so Bob can do an action, and this action can create an irreparable damage, and in mission critical scenario it can cost human life. So for this reason, we need something to fix this case, and note that FIFO channel that we have discussed in the first lecture, and there is also an exercise on it, and there will be solution loaded on the website, do not help you. Why do not help you? Because FIFO channel are just ordering messages that are exchanged point to point. So what you have with FIFO channel is just a channel, and you have that if I send to someone with this channel that is point to point, so you connect just one with another, a message A and before a message B, then you deliver message A before B. So messages are delivered in order, but just on a channel. And FIFO order is preserved because Bob delivers the message of Karen in the same order in which Karen sent it. He delivered the message of Mike and then the message of Bob. And so for this reason, we have to create something stronger because FIFO point to point does not save us. And the idea, the goal of this lecture is to create a way to build a timestamp that can actually order event and avoid this kind of scenario in asynchronous systems. And the idea is to use causal relationship. This has been invented by Lamport, and this was one of the paper that is the most famous paper on Lamport. You can see the original version that is linked on the website. And the idea of this causal relationship is given by two simple rules. The first rule is that if two events occur at some process, for example, to send event, then the process, the order in which the process sees the event is the same order at which the event are happened. And this has a local event that happened in a process. So remember, they can be send event or receive event. And in this case, we say that event E0 happens before event E1. And in our terminology, we will use an arrow, and we will use an arrow with subscript I or subscript 0 in this case to indicate the ordering of events that happen on process P0. So in this case, we say that event E0 happens before E1. And then when a process sends a message to someone, we also have a causal relationship, and we say that the send of a message always happen before the receive of a message. So the send event of message E prime, that is the send event of a message M, happens before E2, and E2 is the receive of a message. And there are physical reasons why this rule holds, and I cannot prove you that they hold. They are just hold for physical reason. The first one is that your times goes in always, is increasing, and so if you see some event that happen at one after the other, then they really happened one after the other. And the second things holds because communication, you cannot go faster than the speed of light. And so if you send a message, then the receive of a message has to happen after the send. You cannot receive something before someone send you because it does not make physically sense. It's as you are receiving something from the future that does not make any sense. And so thanks to this rule, we can create an happened before relationship between events that are causally related. So we say that an event E and E prime and another event E prime are related by an happened before relationship, and we use the right arrow if the following three things hold. One of the following three things hold. The first one is the local ordering. So two events, one happened before the other, if there is a process that observes them one happening before the other. So in this case, event E0 and event E1, we have that E0 happens before E1 because P0 observe E0 before E1. And this is, we call it local ordering rule. Then we have the send receive rule, that is the one that I explained to you. And so we say that given two events that are the send and the receive of the same message, we send that the send is before the receive. And so the send receive rule is the one that connects E1 with E2 in this case. And then we have the other rule, that is the transitivity rule. And the transitivity rule says that if there exists an event E2 such that E happens before E2 and E2 happens before E prime, then E happens before E prime. And this just say that this relationship is transitive, and this relationship is capturing causality. Why? Okay, let's see this example with 4 events. So E0, E1, not P0, then P0 sends something to P1, create event E2, the receive event of this message, and then we have event E3. So we have that E3 causally depend on E2 because for the local ordering rule. So event E3 happens is created on process P1 and is created after event E2. So event E3 is created after event E2. So E2 happens before E3. Then we have that E1 happens before E2 because there is the send-receive relationship. So the send of the message happens before the message. And then we have that E1 happens before E3 for transitivity, because there is event E2 that happens, and event E2 that happens is the event that is connecting E1 with E3 in a causal relationship. So with causal relationship, what we mean? We mean that event E3 could have been generated causally, but by event E1. Okay? And also always for the transitivity rule, we can show that event E0 happens before E3. And this means that we are creating a causal path that connects E3 with E0, and all the events on this path are in a relationship that is happened before relationship. And using this happened before relationship rule, you can build a partial ordering between events. So what does it mean? It means that there is always couple event in the system. It's possible for which the causal, the happened before relationship does not hold. So in this case, let's, okay, there is a typo in the text. You have to read if E4 and E3 are not in happened before relationship, then they are concurrent. And in this case, in this figure, we have that after event E1 on process P0 happens something that is E4, but there is no happened before relationship between E4 and the E3. Why? Because when you create E4, after the send of E4, after the creation of E4, you don't have any event that connects E4 with E3. And so it means that E4 is not influencing E3. So E4 cannot causally influence E3, and vice versa. Also, E3 cannot influence E4, if you think about it. Anyway, you can use the happened before relationship that I explained, and you will see that you cannot find the unhappened before relationship between E4 and E3. So another way to see it that does not exist an happened before relationship is that the only way to connect E4 on E3 is going backward in time. And this is not possible. And so we say that the ordering of event on your system given by the happened before relationship is partial because there are this concurrent event, and this concurrent event cannot be ordered. This is important. And so the happened before relationship is just a partially ordered set. So you don't need to know what a partially ordered set is. It's just a mathematical formulation to say that is a set of elements such that there is no total ordering between the elements. So there could be elements that are not comparable. And this is an example of happened before relationship in a bigger system. You can see that we draw two lines, the red one and the green one, and every event on the red line is connected by an happened before relationship, and also every event on the green line is connected by an happened before relationship. Notice that we could draw other line, so we will try to create a blue line or other line by intermixing these lines, and so this is just an example. But let us see on the red line. The red line tells us that the last event on process 2 is causally influenced by any event that happened on the red line. So what do we mean with causally influenced? We mean that if we don't know the semantic of the algorithm, then any event on the red line could have created the last event on process 2. Because it happened before the last event on process 2, and so the last event on process 2 has seen it in its history all the event in the happened before relationship. You can also look at this in this way. So the the happened before relationship is a worst case causal relationship that just connect all the events that could have been connected by some meaning in your system and in your algorithm. And then we have the green line, and the green line is the same thing of the red line. We have an happened before relationship, and we also have events that are concurrent. So if we take the first event of the green line and the first event of the red line, they are concurrent, by means that the two events are totally independent and they cannot influence each other. So again, what we mean by they cannot influence each other? We mean that the events happen at the same time and no events has knowledge of the other. So if we look at the history of the first event on P1, the history is empty because it's the first. And also the first event of P3, the history is empty because it's the first. And so it means that the two, they cannot influence each other. So it's not possible that when process P3 created its first event, it had knowledge of the event on process 1. So you can see the happened before relationship also in this way. There is an happened before relationship between two events if the last event in the happened before relationship knows the event that happened before. So it knows, or it could knows by the exchanging of messages, that message is happened. So on the green line, the last event on the green line could know that the second event of the green line happened, because there is a connection of messages or a connection of action on the same process that connect the two. And in this case, it's a connection of action on the same process because the same process P1 receive the event E21 because that event is just a receive event. And then he has another receive event, and then he creates a send event. And this send event creates on process P3 the receive event that will be the last event of the green line. So this is what happened before means if you want to look at it in a different way. And now what we have to do is that we will try to create something that is called a logical clock and have been invented always by Lamport. And these things allow us to timestamp event. And this timestamp will have a special property that if an event E happens before E prime, then the timestamp of E will be less than the timestamp of E prime. So notice that we are not saying we are not stating anything on the other line, on the other direction of the implication. We just say that this logical clock will be created in such a way that if an event happens before another, then the timestamp of the first event will be less than the timestamp of the second event in the happened before relationship. Noting also that logical clock are not physical clock. So they are totally different from the physical clock. They are totally different also from the software clock. That was the term we were using to indicate a clock that was synchronized by a synchronization algorithm. They are just numbers, and these numbers are just a partial order, are just something that allows you to partially order events. And for the scalar logical clock, we have two rules. So we will focus only on two kinds of events from now. That is the event of sending a message and the event of receiving a message. If you think about it, it's not a restrictive assumption, because in a distributed system, what it matters is when you send something or you receive something. And so what we have, let's assume that we have two processes, P0 and P1, and we have also other processes on the system, and I'm not drawing them, okay? And we have that each process at the beginning, it creates a logical clock that has value 0. And then every time you send something, what you do is that you increase your timestamp. So you increase your logical clock on 1, and you attach this timestamp to your message, okay? And then you send the message. So in this case, we have P0 that starts with 0. Then we have event 0, in which P0 sends something to a process that is outside these two. And what it does is just it increases the timestamp of 1, it timestamp event E0 with this timestamp, and then it sends the message. And the same thing happens with process P1 that starts with 0, then it creates event E1 that is a send that we are not showing, so it's sending something to someone that is different from these two processes. And what he does is just create one, it just increases of one is logical clock. And then we have the receive rule, that is the things that you do when you receive a message. So when you receive a message, this message will have attached a timestamp, right? Because for our rule, when you create a message, you attach your logical clock to the message increased by 1. So in this case, process P0 creates an event E2 in which he sends a message to P1. So before creating the event, what he does is to increase his logical clock from 1 to 2. Then it attaches its logical clock to the message that will be created with event E2, and then it ships the event to the message towards P1. P1 receives the message. It looks at the timestamp inside the message, and the timestamp inside the message will contain 2. It looks at its timestamp, and its logical timestamp it's 1, and then it takes the maximum between the two, and the maximum between the two will be 2, and will increase 2 by 1, and it gets 3. It gets 3, and what it does is that it timestamp its event by 3, the receive event, okay? Because it increases the timestamp by 1 when it creates a receive event. And so now we have to give an argument, at least intuitive argument, on why if we have an event E that happens before E prime, then we have that the timestamp of E happens before E prime. Well, if an event E happens before E prime, then there will be a path in our system, and this path in our system will be a connection of local rules, so two events that are seen by the same process happening in some order, so is the case between event E0, E2. Then we have an edge that cross-cut processes that goes from one process to the other, and this corresponds to a message that is in flight, and we can have any combination of these two things, but there will be a combination of these two events that create a path from the two events that are causally related. So in this case, it's 0 and E4. And then what happens is that we start with a timestamp in event 0, and for any edge on this graph, we use either rule 1 and we increase by at least 1, in this case exactly by 1 in the example, our timestamp. So it means that by going in the path toward the future, when we travel on an edge that has been created by rule 1, we increase the things at least by 1, right? And this is easy to see. And also when we go on an edge that connects two processes, we are increasing by at least 1. Because what we do when we receive an event is that we take the maximum between the received event and the local event, and we increase by 1. So we are still increasing. And this means that your logical timestamp along this path will be increasing. So at every new node of the path that is just an event, you have a timestamp that is greater than the previous. And this is the reason why this property holds. And stop the video, try to think about it, and you will see that is obvious. And this is the same example that we were using before, but with logical clock. So let's do the example on the green line. So we have process P3 that creates the event. Its logical clock was 0, so it timestamped the its event with logical clock 1. Then it sent the event with a message towards process P1. And process P1, in the meanwhile, has created an event itself, and the event is E11, so it increases its logical clock by 1, and then it receives a message, and this is the event E21, the second event of P1. So what P1 does is do the maximum when it receives E21 between its old timestamp, that is 1, and the timestamp attached to the message, that is 1, and the maximum between 1 and 1 is 1, and then it increases its logical clock by 1 because it creates a receive event locally, and so it timestamps the receive with a logical clock that is 2. Then at process P1, always we are following the green line, what happens is that you receive a message from P3, and this message contains something that has been timestamped by a logical clock that is 5. So you can also do alone and try to understand why that event has logical timestamp but is 5. And so on the green line, we receive something that is that has a timestamp 5 and our old timestamp was 2. So what we do is between 2 and 5 is that we take 5, that is the maximum, and then we increase by 1 and we get 6. Note that on the path that we are following, the green path is not, as I said, we increase by at least 1, but we can increase more than 1. So between event 2, E2 and 1, and even E3 and E3 1, so the 2 event on process P1, we increase from 2 to 6. But we increase, and this is important to show why the relationship that of the logical clock holds. Notice also one thing, that since we take the maximum and we increase the maximum by 1, the event E31 will also have a timestamp that is greater than the send event, and the send event was E33, the event on process 3. And this is because the logical clock have to work on any path, and in this case you are merging two casual paths. Try to see why. But in the same case, it does not matter. Even if you are merging two paths, since you take the maximum and you increase by 1, you will be greater than the two events that you are merging on the two different paths. And we are merging the path that contains event E33 and the path that contains event E21, if you think about it. Then we have the event 4 on process 1, event 4.1, and we increase the logical clock of 6 by 1, so we have a logical clock of 7, and then we send this message to process 3. We send this message to process C. On process 3, what you do is that you create a receive event, so you get the timestamp of the message 7, you increase it by 1, and you get 8, and you create a receive event with 8. Sorry, in this case I was not... you do not just take the timestamp, you take the timestamp of the event, you take your previous timestamp that is 6 and you do the maximum between 6 and 7, and the maximum is 7, and then you increase it by 1 and you get a timestamp of 8. So notice that this relationship, this logical clock, works only in one way. So if an event happened before the other, then the logical timestamp will show it. But with events that are concurrent, this timestamp say to us anything. Sorry, nothing. And why? Because take, for example, the first event on P1 and the first event of V3. They have the same timestamp, and this is fine because they are concurrent. But look at the first event on process 2 and the first event on process 3. So even these two events are concurrent because there is no happened before relationship between them, there is no causal path that you can find between them, but still what we have is that their timestamp are not equal. So one is greater than the other, but the events are not causally related. And this is because, as we said, scalar clock can only guarantee the following property, that if E happens before E prime, then timestamp of E is less than timestamp E prime. But they do not guarantee the other way around. That is, if the timestamp of E is less than E prime, then with only logical clock, we cannot say that E happens before E prime. See the previous slide and go again on the previous slide and understand why this happened. So we need something more powerful, and we want something that allows us to fully capture causality and to say that a way to timestamp things in such a way that if we find an event that has a timestamp that is less than a timestamp of another event, then we can say that these two events are causally related. And these are the vector clock that we will explain in the next video.